In this video, or for this lesson today, we're going to talk about the normal distribution. Um, we've already talked about the normal distribution, so this should be reviewed. And the main thing that I want to talk about is going to be how do we calculate the normal distribution or our normal probabilities using the Inspire now that we have access to that. So the learning intention for today is I want you to be able to explore. We're going to explore the properties of the normal distribution. And I want you to identify and calculate. Big thing I want you to be able to do is calculate normal probabilities. And again, like I said, we've done this. You've seen it, and you'll remember it more when I start showing you the normal tables. So we've done this part of this before, but we're going to introduce you to the calculator today. And so your success criteria for today is I can define the parameters of the normal distribution. And remember, your parameters are what we call the true population value. These are the true population values we're looking at. All right. And then we're going to label and shade normal curves. So we're going to draw these curves and we're going to learn how to shade them. And the shading is going to help us use our calculators because then we want to be able to calculate the normal probabilities. And I'm going to introduce this topic or bring you into it using the SAT. Most of you probably have taken the SAT or you will take it at some point. And so here's what it is. The SAT is a standardized test. And when we talk about the word standardized, it tells me the shape of the distribution. Remember, there are three shapes. We have the left skewed shape, right skewed, and the symmetric shape. A standardized test is a symmetric and unimodal. The word symmetric, recall that this word symmetric just means that your mean is equal to the median. So that's the first thing I'm saying. The mean is equal to the median. When we add this unimodal curve, unimodal means it has one peak. So there's one peak and it's symmetric. So everything starts to fall from the peak. When you get that, you get your bell shape. And the bell shape introduces to the normal distribution. So your SAT is made up of two scores, a math score and a verbal score. They're both normal. And when we combine those two scores, it turns out that you also get another normal value. And so when we look at the overall SAT, here's what you need to know about it. The mean of the SAT, when you combine scores, is a 1051. So we call the mean, remember, mu of x. That's called mu of x. And that's equal to 1051. It's a Greek letter, which means it's a population value. That's a population value I'm looking at. And then the standard deviation is 211. Again, we call the standard deviation sigma x. That's equal to 211. And that's another Greek value, a Greek letter. So it's another population value. And remember I talked up here, the population value is called a parameter. So these are the parameters for the normal curve. Actually, you are hoping to get a scholarship to your dream school. In order to qualify for the scholarship, you must score at least a 1320. At least a 1320. I want to know what percentage of people who take this test score a 1320 or better. And so remember, because the shape is unimodal and symmetric, this is a normal curve. And recall that in a normal curve, the normal curve is unimodal, which means that it has one peak. It's unimodal with one peak. And it's also symmetric. Symmetric meaning that we have a mean equal to a median. And because it's unimodal and symmetric, so unimodal meaning one peak, here's your peak. Symmetric meaning that from that peak, everything falls like this, to that shape. The mean of this curve will always sit at the center or the middle of the curve. Because it is at the middle, remember the word middle, that's why our mean equals our median. That's why our mean equals the median. And so in this particular case, mu will always sit here at the middle. And in this case, our mu is 1051. That's 1051. And there are, if you recall, there are 6 standard deviations underneath this curve. There are 6 standard deviations underneath this curve, 3 to the left. Remember, your standard deviations are the points of inflection where they start to drop at. So they're here and here, here and here, and then here and here. And we know in this particular case that we have a standard deviation of 211. So to get the values, if I want to get the values to the right, I'll take 1051 and add 211. So I get a value of 1262 for the first standard deviation Add 211 again. 1473 for the second standard deviation to the right. Add 211 again. 1684 to the third. If I want to do the left-hand side, I take 1051 and I subtract off 211. I get 840 here. Subtract off 211 again. I get 629 here. And then subtract off 211 one more time, and I get 418. So remember from the empirical rule, by the way, 3 standard deviations, that's 99.7% of the data. So most people score within these values. But we have 3 to the right, 3 to the left, so that's 6 standard deviations underneath this normal curve. The other thing you need to know is that the tails extend to negative infinity on the left and positive infinity on the right. So what that really means is that this curve, this tail over here, is going on forever. This curve over here, this tail over here is going on forever. On the left, we call this negative infinity. On the right, we call it positive infinity, right? Call it positive infinity. And then the big thing that we're focusing on now is that the area under this curve, that's what I'm really interested in. This area underneath the curve is what I actually want to find. The area underneath that curve is equal to 1. And we're going to calculate that because it's equal to 1, we can find percentages or probabilities based off of that. And so when we talk about this curve, we're going to first start off by defining the parameters. So the parameters for a normal distribution, here's how we define it. Just like we did in the binomial, we're going to say that x follows a normal distribution with 2 parameters, a mean mu of x and a standard deviation sigma x. Notice that once I knew the mean and the curve, I could set the mean and the standard deviation, I could set this entire curve up. So because I know mu of x and sigma x, I can set the entire curve up by adding and subtracting the standard deviation from the mean. So in this particular case, for this problem, we know that the SAT scores are normal with a mean of 1051 and a standard deviation of 211. And now I want to know what's the probability that you must score at least. What does the word at least mean? When I think of at least in terms of symbols, at least means I can get that score or something bigger than that. So we write that as a symbol. I want to find the probability that x is greater than or equal to 1320. Right? And so when I do this, I'm going to go on my curve and I'm going to look here at 1320. 1320 falls somewhere right here. That is 1320. I want to be at least that value or something more. So I really want to find the probability you fall back to the right of this value. I want to find the probability you fall back to the right of this value. And we know that, so one way we know how to do this then is using our z-scores. We know how to find this using a z-score. And so remember that a z-score measures, let's come over here and fill up that part of the notes. These are normal tables. But recall that a z-score gives the number of standard deviations. So the number of standard deviations below or above the mean of value lies. If it is a negative z-score, negative z-scores are below the mean. And positive z-scores are above the mean. And our z-score formula, remember, is z is equal to x minus mu divided by sigma. So again, I can find a z-score of any curve if I know the mean and the standard deviation. And so if I want to find the z-score for a score of 1320, with this mean and this standard deviation, we just do z is equal to 1320 minus 1051 divided by 211. And I want you to notice here that because this value is positive, because that value is positive there, because your 1320 is bigger than 1051, our z-score is also going to be positive here. Our z-score is also going to be positive. So let's calculate that z-score. 1320 minus 1051 is this, divided by 211. 1.27. So this is equal to 1.27. And remember, on a z-score says for measuring standard deviations above the mean, but we've set the mean now on a normal, standard normal is what we call this. Set the mean at 0. And then we have standard deviations of 1. So 1, 2, 3. And so in this particular case, we're at 1.27 for our z-score. So that means that we are 1.27 standard deviations above the mean. So a score of 1320 corresponds to a z-score of 1.27. And now remember when we did that, so I know my z-score here is 1.27. I actually want to find the probability of having a z-score that is greater than or equal to 1.27. These things are the exact same thing. This is on a standard normal. This is on the curve that I'm dealing with. And because this is on a standard normal, I can use my standard normal tables. And so to do this, what we would do is we come up here and we look, and remember we go find 1.27 on this table. So when I find 1.27, 1.2, and then 0.07, I get 0.898. But the problem with that is we can see that when we look at this particular curve right here, this is not almost 90% of the area, right? This is actually smaller than something 50% because the mean is 50%. So this is nowhere near 90%. And that's because when we look at this curve, remember, this curve that we're looking at on our table only gives us the right-hand side. The left-hand side. I'm trying to find the right-hand side of the curve. So right now that it's saying that the left-hand side is 0.898. So in order to find the right-hand side, I need to subtract that from 1. If I subtract that from 1, I get 0.102, and this will give me the right-hand side. And that answer makes a lot more sense. And remember, a simpler way to do this was to actually just look at the negative version of that. If you look at your negative version of negative 1.27, you get this value here, 0.1020. So we can do it that way too. But what I want to do now is I want to get away from the tables. In order to get away from the tables, I want you to use your calculators. And when we talk about using the calculator now, then we're going to have to start drawing these curves. Because when I draw this curve, what I see now is that I can calculate this area right here by bounding it by some numbers. And in particular, I'm starting my bound at this value of 1320. And I'm going to go, because this goes on forever, it's going to positive infinity. And my calculator can actually do a process of integration for us. It's going to integrate. So when it integrates, it can actually take the bounds and find the area underneath the curve at that particular bounds. So in order to do that, we're going to draw these different curves now. And we're going to shade these curves. And you have 3 different types of curves you can shade. And we have what's called the lower shading, or a lower left tail. We have area to the left. In this particular case, here's what happens. Every curve has a lower bound up to some upper bound. And the lower bound on this particular curve says, well, if you start, where's your shading starting at? It's starting on the very left, but this left goes on forever. So technically it starts at negative infinity. And it's going to stop the shading at whatever this z-score is. So my lower bound here is negative infinity, and my upper bound is whatever that z-score is. So this time I'm reading lower to the upper. That's called a lower tail. And an upper tail, this time your shading starts at the z-score, and then it goes all the way up to on the right-hand side. So this is positive infinity. And then from there, we're going to go from, this one says start at z and go to positive infinity for the curve, right? And then the last kind of curve is what we call a between curve. And when we talk about a between curve, we're looking at between 2 z values. And when we do that, it's very simple because we can see that our lower bound is the first Z value, and our upper bound is the second Z value. So we go from Z1 to Z2. Now, this is good, and this is what we need to do. We're going to draw these curves. But the problem with drawing these curves is that we're using these infinity signs. And my calculator wants to have bounds. Infinities are what we call boundless. They go on forever. So in order to bound these things, we actually need to give them a number. Well, in the calculator, you'll see we just need to trick the calculator to think that it's dealing with a really small number when we talk about negative infinity, and a really large number when it's talking about positive infinity. So in order to bound these things, what we're going to generally do is we're going to use a really small number. Well, a really small number for us is going to be something like this. This is what we consider to be a really small number. You can use as many nines as you want to back there. It just needs to be negative. A really large number is something like this. And what we're doing is we're approximating some kind of infinity, or tricking the calculator to think that it's going to a very large value that it'll never reach. And so when we do this in our calculator then, so now that we can draw the curve, when we draw the curve, we can come back and look at this one here, and we can see that, well, this curve is a upper curve. It's an upper curve. It's bounded by this value of 1320, and it's going on forever to positive infinity. So this is going to be bounded with a lower bound of 1320 and an upper bound of positive infinity. And now I can go to the calculator and actually do this. And in my calculator, I'm going to use a new function called Normal Cdf. And we only use Normal Cdf when we want to find, you use Normal Cdf to find percentages, proportions, or probabilities. That's when you use Normal Cdf to find percentages, proportions, or probabilities. Those are all the exact same things, but you're going to use the Normal Cdf to find it. You have in your calculator to find Normal Cdf. This is located under Menu, 6, which is Statistics, 5, which are Distributions, 2, which is Normal Cdf. For the normal function, remember in the binomial, we have a PDF and a CDF. For the normal function, you also have a PDF and a CDF. In the normal function, though, you will only use the CDF. Remember, PDF means exactly. When we try to find area at exact values, that does not exist. There is no width to find area at an exact value. So we can't find an exact PDF for this particular distribution. We never use the PDF. We never use the PDF. So I'm going to add a calculator. I'm going to press Menu, Statistics, number 5, Distributions. And notice here I have a PDF and a CDF. Never use the PDF. We only use the CDF. So using the Normal Cdf, here's how it works. The Normal Cdf wants you to get 4 things. So in Normal Cdf, it wants a lower bound. Where does your shading start? It wants an upper bound. Where does your shading end? It wants a mean and a standard deviation. So what we do first is we always draw a curve. And so when we draw these curves, I'm going to decide if I'm shading upper or lower. So this says a score that is greater than 1320. So when I draw this curve, shade it. Here's what I need on my curve. I always list the mean on the curve. So here's 1051 on my curve. So here's the first part, 1051. That's on my curve. And then I decide I want to be greater than 1320. Well, where does 1320 fall at? Well, it falls to the right of 1051. And because I want to be greater than that value, I'm going to shade this to the right. I'm going to shade that to the right. Now, from here, the first thing I actually should have did was I should have defined the parameters. So X follows a normal distribution with a mean of 1051, standard deviation of 211. Define your parameters. And now once I have this defined, this picture drawn, all I need is a probability statement. So I'm going to say the probability that X is greater than or equal to 1320. And from here, I'm going to go to my calculator. So in my calculator, I'm going to type in this here, and I'll write it out first before I type it. I have Norm CDF, the CDF, my lower bound. Well, my shading starts here at 1320. So that's the lower bound of this curve, 1320. My shading is going to go to the right all the way to infinity. But remember, my calculator needs a number for infinity. So I'm going to put a bunch of 9s back here. General rule is you need to put one more 9 than whatever your mean is. So if my mean has 4 numbers in it, I need to have at least 5 nines. I need a mean for the standard for this particular distribution, which is 1051, and a standard deviation, which is 211. If I type this into my calculators, let's go type that in. Lower bound, 1320. Upper bound, 99999. At least 5 of them. Put as many as you want to. You can put as many as you want to. The mean is 1051. Standard deviation is 211. When I press OK, notice this gives me a value of 0.101. So about 10%. If you go back to what we did with the z-score, for the z-score we got 0.102. So we're pretty close to being at the same value there. So if you go back to our z-score, we get a value of 0.101. Come back to our z-score. We said that when it was a z-score, when it was probability greater than equal to 1.027, this was 0.102 from the chart. Well, here we're getting 0.101 from the actual calculator. The calculator is more accurate, actually. So let's look at the next one, which says having a score that is less than 900. So the first thing I'm going to do, I'm going to draw my curve. 900, put the mean on it at 1051, and 900 is on the left-hand side of this. If I want to find a score that is less than 900, I'm shading it to the left. This is a lower tail area that I'm finding. It's the left-tailed area. So to do that, this is the probability that x, I have an x value now, has to be less than or equal to 900. And in this distribution, we always use the less than or equal or the greater than or equal signs because they mean the same thing as less than or greater than. So we're always going to use less than or equal or greater than or equal to write our statements. When I write this statement, again, it's Normal Cdf. The lower bound here starts at, your shading starts way out here at the negative infinity. I need a number for that, so I call it negative 999. I need 5 of them. It goes up to 900, and we have a mean of 1051 and a standard deviation of 211. So when I go to my calculator again, remember I go menu, 6, 5, always the CDF, so 2. The lower bound here is negative 999. The upper bound, 900. The mean, 1051. Standard deviation, 211. Type it in, and I get this value here. So this is equal to 0.237. And so the next one then, it says between 1950 and 1200. Well, again, what I'm going to do, and that shouldn't be 1950, that should be 950 actually. So I'm going to change this to 1051. I want to be between 950 and 1200. So 950 falls on the left-hand side, 1200 falls on the right-hand side. I want to be in between those two values. So this is normal CDF. Oh, I'm sorry. This is the probability that X is, and here's how we write in between. We want to be in between 950 and 1200. Here's how you write a between statement. So you want to be between, and again, I'm sorry I didn't show this, but having a score between, it said 1950, change that to 950 and 1200. We want to be between, draw your curve. So you're between, remember, leave your curve with 1051. You're between 950 and 1200. So you're shading inside of here. You write that statement like this. You want X to sit between those two values. Here's how you write that. Your lower bound is 950. Your upper bound is 1200. And so again, this is normal CDF. These betweens are actually easier because you can see them better. There's no changing anything. That's 950, 1200, 1051, 211. So when we calculate that, 950, 1200, 1051. So again, I'm going to go menu, 6, 5, 2, 950, 1200, and 51, and 211. Here I get a value of 0.444. So the first part of this part is drawing these curves and then find those probabilities. If you look at the next type of question, though, the next type of question, it says, what score will put a person in the top 5% of all scores? So the next question says, what will put a person in the top 5% of all scores? Well, this is different because what we've been doing is trying to find the percentages so far. Here I'm given a percentage, and I want to find the score for that percentage. We're actually going backwards. And when we go backwards, we use what's called the inverse normal. The inverse normal. And this is used to find x given a percentage or a probability or a proportion. So I want to be in the top 5%. So the first thing I'm going to do is I'm going to draw a curve. And I'm going to label this curve with my mean, which is at 1051. But this time I want to be in the top 5%. So if I'm in the top 5%, that means I have to sit on the right-hand side of the curve way out here. Top 5% means there's only 5% of people who have scored better than me. That's what that really means. And so the inverse normal can calculate this, or I can try to calculate this. But the problem with this is the inverse normal can only calculate the left tail of this particular distribution. So the inverse normal can only calculate this side over here. But that's okay, because if this is the top 5%, the inverse normal only calculates the bottom of something. But the top 5 also corresponds to the bottom 95. So all I have to do is look at the left tail. And if this is the top 5, right? Top 5, this X separates the top 5 up here, the bottom 95 are back here. I always need to look at the left tail, and the inverse normal says, in this function, it is inverse norm. It wants a left area. It wants a left area expressed as a decimal. So in this case, we're going to do 0.95. Then it wants the mean and the standard deviation. So here, my inverse norm, and you don't need probability statements for this. You're not finding probabilities. You're actually just finding a value of X. So your value here is going to be the bottom 95, which is 0.95. The mean, 1051. Standard deviation, 211. And so to get to this function, this will be menu 653. This is 653. So when I go here, menu 6, 5, inverse normal 3. It wants a left area expressed as a decimal, 0.95. It wants the mean, 1051, and the standard deviation, 211. Do that. I think I messed it up. Menu 6, 5, 3, 0.95, 1051, 211. Okay, yeah. So this tells me that an x value approximately equal to an x value that is equal to 1398. Next value equal to 1398.06. We'll put a score in the top 5% of all values. A score of 1398.06 will put a score in the top 5% of all values. E asks what will put a person in the bottom 10% of all values. So again, what we're going to do is we're going to draw a curve. And on this curve, label the mean at 1051. I want to be in the bottom 10, so I'm down here this time. Bottom 10 means 10% have scored below me, or I've scored better than 10%. So this is the bottom 10%. And notice what side this is on already. It's on the left, so we already have a left tail area here. So we don't change anything. So this is inverse norm. 10% of the decimal is 0.1. Your mean is 1051. Your standard deviation is 211. So when I calculate this, again, menu 6, 5, 3. I'm already on the left, so I'm going to leave it at 10%. The mean is at 211. I mean, mean is at 1051, and my standard deviation is at 211. That's okay here. I see that a score, an x equal to 780.593. A score of 780.593 puts me in the bottom 10% of all scores. So we use the inverse when we're going backwards. The inverse this is a backwards function. So if I want to find an actual x value, I use the inverse. So again, we're going to use these calculators, and I want you to practice with this. I'm going to give you a sheet to practice with this on, where you actually do problems and you're going to calculate these. Make sure you draw curves. Curves are going to help you see what you're actually plugging into the calculator, right?